Hello and welcome to this presentation towards highly automated machine learning empowered monitoring of motor test stands. My name is Diego Botache and I'm a PhD student at the University of Kassel, and this is a joint work between three research groups, namely Intelligent Embedded Systems, Electrical and Electronic Automotive Systems, and Digital Technique. The evaluation process of electrical traction machines is very complex and prone to failures. This is due to the many factors influencing the performance of the machine, and experiments are time consuming and downtimes in the system are very expensive. Dedicated test bench allow the evaluation of new machines under controlled conditions, but deliver a high degree of data coming from a multitude of sensors in the test bench. There's a little work actually targeting the functionality of the test bench itself, and only risk assessment and risk reduction regarding the ISO 12100 requires only functional safety of test stands. So emergency stops are actually triggered when dedicated sensors exceed a predefined threshold. Sensor malfunctions in the system or downtimes cannot be recognized in that way. In our machine learning empowered monitoring, we aim to optimize the development cycle of electrical machines, monitoring the system based on the provided heterogeneous time series data and applying different machine learning techniques, machine learning methods, which should include also a self-optimizing cycle for adapting to changing conditions in the system, different operation modes, and also delivering information to the human operator for fault identification and also for taking preventive actions in case of possible faults. So the main goal is the optimization of the experimental process and avoidance of costly test bench downtimes. So in the following scheme, I want to provide you some of the data that is acquired from the test stand and some of the devices available in the test stand. So from the power electronic side, we have some internal currents, voltage, power, and temperature sensors. We also have at the load machine some temperature sensors at the rotor, stator, and bearing, also vibration sensors and RPM and torque. At the measuring shaft, we have also revolutions per minute and torque. At the water cooling system, we have temperature and the flow rate. And finally, the automation system communicates with all of these devices using a CAN, and it provides also some status signals and target values for the experimental process. Now let's take a look on the overall concept, and this can be divided into two basic sub-processes, so the offline process and the online process. At the offline process, we start with the efficient data acquisition and providing a database for training the first models. At this stage, we have signals with a sampling rate from 10 to 100 Hz. The labeling process should be also include the definition of some predefined failure types, upsampling and scaling process to generate a consistent input space and data storage into a cloud server. The training and design of the models should be done in GPU cluster, and it should also include a self-optimization cycle for hyperparameter optimization. Then we go to how I optimize the implementation of the generated models into FPGA, and in this second sub process and the online process, we include the generated hardware implementation of our machine learning model to continuous monitoring the state of the system, to provide feedback to the human operator, and he will be able to take maintenance actions to avoid downtimes in the system. It will also provide information for labeling unknown instances, and depending on the condition of the system, also maybe updating the parameters of the models. So now let's get closer to the techniques that we want to apply into our machine learning empowered monitoring. And this is at its core the most important part in the context of self-X systems. And I have divided that into 5 different fields of investigation. So the first field consists actually on the self-management process, and it consists on the efficient data acquisition, the labeling process, and providing databases for training machine learning models. Also the continuously update of the training data, depending on some conditions, maybe changing conditions in the system. At the second stage, or the second area, the self-optimization area, we should be able to select different deep neural network architectures, and also to optimize hyperparameters using techniques like Bayesian optimization techniques or grid search or random search. Then we have the failure detection and classification, and this is the first stage for providing the system the ability for self-awareness and detecting and delivering information about the actual and the current state in the system. For this, we have generated a set of defined fault types which we use for training a model in a supervised manner. But since we are not only interested on detecting faults in the system, we want also to predict them, and emerging faults in the system, we want to predict them for avoiding downtimes in the system. So we need to also apply in the fourth area predictive monitoring approaches, and this can be, for example, be done using probabilistic forecasting of critical sensors in the system. The last area of investigation is the self-organization area, and this is the most important part because we are not able to model any kinds of faults in the system, or every kinds of failure types in the system, and these unknown instances that are actually don't belong to the training dataset or belong to a different distribution of the dataset should be detected using anomaly or novelty detection techniques. Using the feedback from a human, we should be able to define if this is a fault or it is actually on, for example, a domain shift in the system. And if it is not a fault, it should be included. These unknown instances should be included into the training process and should be then updated into the databases. Also, if we have a fault in the system, then we should apply suitable root cause analysis and explainable AI techniques for supporting the identification of new failure types. The optimized hardware implementation, that this is due to the complexity of the deep neural network models that we want to apply, that we aim to apply in this framework. We assume that optimizing the models in dedicated hardware will also increase the performance, and we also meet requirements of the test bench. So this can be divided into two stages, and the first stage is upper on this picture, which consists actually on finding a representation of the parameters of the model and quantization of the parameter models, which are then given in the single layers of the model, then training, and at the second stage down with the name Elysia, using the parameter sets that we have chosen in the first stage, we want then to optimize the data flow and the structure of the model, and then also optimize the arithmetic units in the model to provide then and optimize the hardware implementation in an FPGA. Now let me explain the first case study, and these are the first results towards our monitoring approach, and they are focused actually on the self-management, self-optimization, and failure detection and classification areas. So now let me explain the first fault cases generated in the system for the design of a classification task. And these fault types are clear examples of faults that cannot be detected with common threshold-based approaches. For visualization purposes, the sensor values and the plots are actually scaled. The first failure type, the rotor temperature fault, it was actually caused for build modifications in the test bench. So we didn't actually wanted to create this failure type, but after some modification in the test bench and after some test runs on the system, we just see that one of the sensors provided implausible values in the range of 1 and 2 degrees. So at the left side, you can see that the temperature at the rotor from the load machine changes depending on the operation mode, and at the right side, it actually keeps the value of in this range of 1 and 2 degrees. For the failure type number 2, we uncoupled one of the vibration sensors from the load machine, And after left side, you can see that increasing the velocity of the device under test also increase the value of some of these vibration sensors. It also highly depends on the behavior of the device under test, but at the right side you see that actually the values of these sensors barely increase, and also in an idle stand they still deliver very high values. For the cooling fault at the load machine, a simulated failure of the water cooling was given. For the operating point shown here in these two plots, we can see that at the right side the temperature, and this is using the same time scaling in the plots, we see that at the right side the temperature increases a little bit faster than at the left side, and also a new operation mode of the cooling machine actually doesn't decrease the temperature of the sensor, and it keeps actually increasing. So you can see at the green and the pink sensor values that the flow rate is actually increasing, and the behavior is actually like and it keeps increasing. And then the last part of this experiment, you can see a shutdown of the machine, and you expect actually that the temperature of these sensors actually decrease and varies very fast, but at the right side you see that they decrease actually very slow. Finally, we have an active short circuit, and that's a very particular failure type, because this is caused actually from the side of the device under test. So this is actually not caused from any of the sensors in the system, but this is a state of the device under test which is actually triggered when some damage or when something happened in the system to avoid high damage of the machine. And as you can see, at this operation mode, we have a freewheel operation mode. We don't expect a very high torque value of the machine. So actually only when we increase the velocity of the device under test. But at the right side you see that we have actually a lower values of the speed than we have very high torque values. Let's go briefly to the pre-processing and feature selection process. And signal groups provided from the system, we categorize first these signals into sensor signals and categorical signals, and with some up and down sampling strategies we put them into the same sampling rate. Then we use a simple feature selection strategy using an XGBoost to select 50 relevant features, and then with a sliding window strategy we just extract segments from the time series, and this is actually what we use for training the models. In our first experiments we started with some CNN and LSTM structures, but the most sophisticated structure is actually this inception time structure, which represents one of the state-of-the-art in approaches for time series classification. We keep actually most of the parameters actually constant, and also we refer that to the paper of the inception time. So first go to the failure detection, and in this case we joined all the failure types together into a single class, and we want to perform actually only the failure detection itself. And you can see that the inception time architecture with a sequence or a segment length of 4 seconds improves its best, and this is shown on the right side in the confusion matrix, and you see that the normal state were confused actually only with a 19.7 misclassification rate. For the failure type classification, and this delivers actually the most important and critical information for upcoming experiments. You can see that the classification of the failure type 2 and 3 were the most challenging part of this process, and it can have many possible reasons. For example, the low sampling rate of 100 Hz of the signals, and maybe possibly also the short sequence length of the segments. But now, and this is actually a spoiler alarm for the upcoming experiments, we increased actually the segment length up to 2 minutes, and we have shown that actually the performance of detecting the failure type number 3 didn't really increase. But we noted that in the data, and the time series data accurate and the test stand also contain some data with a different load machine. So this was a very critical aspect, because after separating these two datasets from the two different load machines, we could see an increasing of the performance of the detection of failure type number 3. So this is very relevant, and we need to show specific criteria for recognizing these domain shifts. And this is actually clearly advised for a domain shift in the system with a new load machine. And we need to trigger an event for updating the parameters of the model. So the labeling process was critical at this point, and it required an additional update of modifications devices as a label on the data. In the second case study, we have shown a work width reduction of one very small tiny darknet, and due to the hardware resources that were able at that point, was not possible to implement the presented models for the classification task. But we have shown here, and this results the imminent potential of this approach, and this was actually done automatically and changing parameters in this process. So we could reduce actually the memory resources of the tiny darknet up to 55%. Now let's go to the outlook on future work. So we have shown an efficient framework for data acquisition and machine learning monitoring. The results for failure detection and classification demonstrates the eminent potential for optimizing the development cycle of electrical motors. An extension to fault prediction and probabilistic forecast is required for also detecting emerging faults in the system. Detection of unknown instances, like using out of distribution techniques or uncertainty modeling, are required, and including also the knowledge of the human experts. We need to define some criteria for defining domain shifts in the system, to triggering update of the models in the system, and a suitable root cause analysis and the application of explainable AI techniques are also required for supporting the labeling process of new failure types in the system. Finally, the hardware optimized implementation of the presented models is required, and also the evaluation of the mean detection time and inference time, and also the evaluation of the classification performance compared with all models only in the GPU servers.